An additional instrument on GOES that we have not yet discussed in detail is the Geostationary Lightning Mapper, or GLM. It detects lightning flashes over a large disk, something that no other instrument is capable of doing. This module will describe how GLM works and discuss global lightning distributions. The detection of lightning has several benefits. From a research perspective, a long time period of lightning data can inform about how the electrical field balance on Earth evolves. Lightning is also an important indicator of intense convection and reveals some information about the microphysical and dynamical structures of clouds. For example, many have associated lightning and tropical cyclones with intensification of the storm because it signifies the existence of intense updrafts. Lightning detection has economic and societal utility as well. For example, it can provide early detection of developing severe thunderstorms. Ground-based lightning detection systems, the subject of the next module, provide warning of nearby electrical activity or augment the research capabilities of lightning detection from space. An exact understanding of how lightning occurs has not yet been reached, but the basic mechanism is as follows. Here's a cloud that may become electrified, and here's a person on the ground. The ground tends to take on either a negative or a positive charge, while in the cloud, ice collision processes cause negative charge to accumulate in the middle to lower portions of the cloud as the larger falling graupel becomes negatively charged, while smaller rising ice crystals and updrafts become positively charged and are lofted to the top of the cloud. A thin layer near a cloud base is also sometimes positively charged. The ground may be positively or negatively charged, like said before. Lightning occurs when a large electrical potential develops. This may occur between opposite charges in neighboring clouds, within a single cloud, which is known as intra-cloud lightning, or between the cloud and the ground, known as cloud-to-ground lightning, or CG. In this example, the lightning begins as a leader, extending from the negative charge in the cloud toward the positive charge near the base. The negatively charged leader fills the positive charge and moves down toward the surface. As the leader approaches the surface, the electric potential near the ground increases, and an upward streamer can develop where the potential is greatest. The upward streamer meets the downward leader, and discharge occurs, reducing the electrical potential. This is the visible lightning flash. During this flash, the surrounding air heats up to tens of thousands of degrees, emitting visible light as well as other wavelengths. The charge is then reduced at the cloud and ground until it rebuilds. The annual mean lightning strike frequency globally is shown here. It is actually derived from a ground-based network of sensors, since we have not yet had continuous global detection of lightning from space. Lightning is more frequent over land than it is over the ocean, particularly over northwestern South America, the southeastern US, Central Africa, and the maritime continent. Less lightning is detected out over the ocean even where convection is common, such as the ITCZ or the South Pacific Convergence Zone. From space, lightning detection has been limited to a few instruments that observed only small areas at once. For example, the optical transient detector flew aboard Microlab 1 in the 1990s, and the lightning imaging sensor was aboard the TRIM satellite. The GLM design is based on the same concept as the two formerly operating instruments, and is pictured here, in partially constructed form. Because it is in geostationary orbit, it views the largest area of any spaceborne lightning sensor to use today, covering up to 52 degrees latitude. Thus, the major benefit of spaceborne lightning detection is continuous observation of a large area. The main negative is that the spatial resolution, only 8 to 14 kilometer wide grid boxes, depending on distance from nadir, means that precisely locating a lightning strike is not possible. All of the spaceborne lightning detectors work on a simple concept. At 777 nanometers, in the near infrared, there is a narrow oxygen absorption band at which the vertical path direct transmittance to the atmosphere is only about 80%. And that's circled here in red where my mouse pointer is. Oxygen is ubiquitous in Earth's atmosphere and is well mixed horizontally. Therefore, atmospheric emission of near-IR photons at 777 nanometers is dependent only on the air temperature. At normal temperatures, air emits in the terrestrial part of the IR spectrum, around 10 microns. When lightning heats oxygen molecules, the air becomes hot enough such that its Planck emission spectrum shifts temporarily toward much shorter wavelengths. Spaceborne lightning sensors detect the emitted radiation at 777 nanometers by heated oxygen molecules. The instrument itself is very large, as shown here, and it stands almost 5 feet high if measured lengthwise. And one example of GLM data is shown here in this movie. The yellow and orange flashes that you see pop up denote lightning strikes during an evening in the Amazon. About 1/3 of the way through, the collocation right now of lightning and developing cumulonimbus is obvious, and then it gets dark. But the lightning is still detected. Flashes are detected by searching for persistently higher emissions than the background average over short periods of time. The background average is computed frequently. Pixels that exceed this background are considered events, and adjacent events occurring near each other at the same time are considered a group of events. A single flash is a sequential group in space and time separated by less than 330 milliseconds and 1 to 2 grid points. You can see the link here at the bottom for more details and some helpful graphics in understanding the GLM lightning detection algorithm.